Well, welcome back, everybody, and this will be the second part of our biology and behavior chapter. So we will be talking about neuroanatomy, which is the anatomy of the nervous system. And as you'll see, the nervous system consists of many substructures and even smaller structures, and then all of those structures are comprised of the neurons that we had already talked about. So let's go through the nervous system in an overview, and we'll start with these are our two main divisions of the nervous system: the central nervous system, or the CNS, and the peripheral nervous system, that's the PNS. So the central nervous system consists of your brain and spinal cord. So the central nervous system here is the brain and spinal cord in purple. That makes up your central nervous system. You know it's your central nervous system. Those are the neurons that are encased in bones, right? Your brain is encased in a skull, and your spinal cord is encased in your spine. And we have those, the brain and spinal cord encased in bone as protection, because we really don't want to damage our brain and spinal cord. The peripheral nervous system are all the nerves outside the brain and spinal cord that connect your central nervous system to the rest of your body. And so the peripheral nervous system, as you can see here in orange, are all these other nerves that go everywhere, to your fingertips, to your toes, all throughout your body, right? How do you feel something when you touch it with your hand? It's because you've got nerves in your hand. So all of those other nerves are called the peripheral nervous system. Now, we can break the peripheral nervous system into two other sections. So you can see here, it's kind of showing you we've got the nervous system that we break into the central and the peripheral nervous system. And then the peripheral nervous system we can break into two more parts. We call that either the somatic or the autonomic nervous system. The somatic nervous system is involved with all of our voluntary movements. So when you want to move your leg or your arm, etc., that is all your somatic nervous system, the nerves that are important for voluntary movements. And they also connect with your sensory organs, but for our purposes, really voluntary movements. And then the autonomic nervous system, this is a set of neurons that control things that happen automatically. Autonomic, automatic. They control your heart beating, your intestines digesting your food, your lungs breathing, things that keep you alive but that you do not think about, right? Your autonomic nervous system. You never have to say, I think I should beat my heart right about now. It just does it automatically. That's your autonomic nervous system. And then lastly, our autonomic nervous system can be broken into two more parts, into what we call the sympathetic or parasympathetic nervous system. The sympathetic nervous system is your fight or flight nervous system, or your fight or flight response. You might have heard of this. This is what happens when your body is preparing for an emergency. If you could imagine wherever you are right now listening to this lecture, if you look up and there's a bear looking at you, right? Your body is going to react automatically, right? Because it is part of your autonomic nervous system, but you're going to get ready to either fight or run. And by doing so, your pupils are going to dilate so you can see very clearly. Your body is going to send blood to the muscles so you can run or fight. Your body's actually going to turn off some things that are not necessary, like you kind of stop digesting your food because you don't need to spend energy on food digestion at that point. All of this stuff happens automatically when you need to fight or flee in an emergency situation. And then the parasympathetic nervous system is the relax and digest non-emergency state that our body is in most of the time. Typically, we're in a non-emergency situation. Our body is digesting our food. It's keeping our heart beating at just a relatively calm rate. We're breathing at a relatively calm rate. All of that is just our normal non-emergency system. All right, so that's the general idea of the divisions of the nervous system. And in that autonomic nervous system, just to give you a little more example, and you can look at this in your book, the sympathetic, like we said, is your fight or flight response. Your parasympathetic is your equilibrium, your resting state. And so you can see that the two are kind of in contrast. When you're in the sympathetic nervous system, right, you're in an emergency situation, your pupils dilate. When you're in a parasympathetic rest and relax system time, your pupils constrict. Sympathetic nervous system, fight or flight, you increase your breathing. Parasympathetic decreases your breathing. Again, you can see increasing your heart rate when you're in an emergency, lower your heart rate when you're in a normal situation. So these two kind of work in opposition to each other. Most of our time, it's our parasympathetic nervous system that's working, and only in emergencies does this one kick in. All right, let's talk briefly about the spinal cord. The spinal cord is actually a bundle of neurons that allow communication between the brain and the peripheral nervous system. And I'm going to actually go back here just to show you, right? Here's your spinal cord, and it's connecting all of these peripheral nerves. They all end up going into your spinal cord, and the spinal cord is a big collection of nerves that goes up to your brain. And then your brain can send messages down through the spinal cord and then out towards your body. There are three types of neurons. We have sensory neurons. Those are neurons that receive sensory information. That makes sense. And what are your senses? That's your vision, hearing, touch, taste, smell, and convey it to the brain for further processing. So sensory neurons bring information into our body from the world outside, right? Visual neurons bring information in about what you're seeing. Hearing neurons bring information in to the brain about what you're hearing, etc. We have motor neurons. Motor neurons transmit information from the central nervous system to your muscles. So this is information that's going from your brain. Your brain is saying, move your leg, and this motor neuron is going to get the message and then move your leg. So the motor neurons are sending information from the brain to the muscles. And then we have inner neurons that connect the sensory and motor neurons. We do have reflexes, and you're aware of them if you've ever touched something that's burning hot. And your reflexes actually happen without the message having to go all the way up to the brain, because that does take time to get a message to go, let's say from your hand here, because you're touching something hot, all the way to your arm, to your spinal cord, up to your brain, send a message back, etc. And by that time, you would have really hurt your finger. So without input from the brain in a reflex, the spinal cord neurons are capable of creating a very simple reflexive behavior, right? Which is just pulling your hand away when something is hot. Eventually, of course, the brain does process the event, because you do end up saying, ow, that was hot. But this is kind of the process here. You touch a pan that's very hot. It activates a sensory neuron, right? The sensory neuron brings information in saying, ouch, that was very, very hot. It carries information to an interneuron in the spinal cord. Here's our little interneuron right here. And then sends message to the motor neuron, which is bringing information out, saying, please move your muscle, and this muscle pulls your hand away. Eventually, there's a second system you can see right here, that there is the message that is sent back up to the brain. And so again, your brain will get the message and you'll say, wow, that was hot. But it's probably after you've pulled the your hand away. So this is a simple reflex arc. Goes from a sensory neuron to an inner neuron to a motor neuron, and that's the end of it. There is also the endocrine system. This is a system that uses glands that conveys messages by releasing hormones into your bloodstream. And hormones are chemical messengers, again, that are released into your bloodstream that influence different things like your mood, your thinking, your appetite. Many other processes are controlled by hormones. And the key glands of your endocrine system are right here. We have a pituitary gland that's located right in the center of the brain, just under your thalamus. You can kind of see it here. The pituitary gland influences all other hormones. We often call it the master gland, and it plays a role in regulating your growth. The adrenal glands are also very important. They're located on top of the kidneys here. There are your adrenal glands. And they're involved in response to stress, regulation of salt balance. Salt's very important as, in terms of regulating basically all of our body functions. And then we also have a thyroid gland that's located in your throat right here. It's a butterfly-shaped object or gland that regulates your metabolism by secreting thyroxine. This is a gland. In fact, my daughter had a disease that affects her thyroid gland and had to have her thyroid gland removed. So now she takes a synthetic medication that basically is replacing what her thyroid gland would have done. All right, moving to the brain, you're going to read about Christina, who had swelling on one side of her brain due to encephalitis. This impaired her movement and her thinking, because if you imagine when you have swelling in your brain is encased in the skull, and the skull is hard and bony. It does not stretch. So if your brain is swelling, it's really pushing up against that bone and is damaging the brain. And that was causing seizures also every few minutes. And so when nothing else works and you have a very severe brain disorder, sometimes a treatment would be brain surgery, and in this case a hemispherectomy, meaning they removed half of this child's brain. Here is the brain, just in case you want to see what it looked like. Looks just like that. I've had the opportunity myself to hold and do research on a brain, and kind of feels like very hard jello, if you would imagine that texture. And so now let's start talking about the brain. The brain has two hemispheres. Here they are, or two halves. You have a right and a left hemisphere of the brain, and they each control movement and sensation on the opposite side of the body. So your right hemisphere controls the movement of the left side of your body, and your left hemisphere controls the information from the right side of your body. And if you can tell, this is looking down on the brain, so you're seeing the two halves, left and right. And there's this term called lateralization, which means that one hemisphere is more specialized for certain functions. So each hemisphere, although they work together, each hemisphere also has certain specialties where it's like, for instance, the left hemisphere is better at language, whereas the right hemisphere is better at what we say finding your way around or spatial tasks. The right and left hemisphere exchange information through a set of axons called the corpus callosum. So you can see that these two hemispheres, you can look right down the middle here, are not really connected. They're absolutely separate, except there is a bridge deep within here that connects the two hemispheres, so the two hemispheres can communicate with each other. And that bridge is called the corpus callosum. It's a thick band of nerve fibers that connects the right and left hemispheres, and that allows the two hemispheres to work together to process information. As I said already, the right hemisphere controls the left side of the body, the left hemisphere controls the right side of the body. I thought it'd be fun to take a very non-scientific, non-clinical, but fun quiz to assess your brain lateralization. So if you have a piece of paper and a pencil, just answer true, false. Again, this is not scientific, but just kind of fun. Look at these questions. Here's 1 through 10, and just answer true or false. So go ahead, you can pause this here, just write down 1, true or false, and then 2, true or false. You have to pick one, you can't pick both. Sometimes that's hard. So go ahead and pause this here and go through these 10 questions. And now here is the scoring. So you score 1 point for each of the answers below. So if you answered for 1, you answered false, you get 1 point. If for 1 you answered true, you get 0 points. So go ahead and score this. You can also pause this here for a minute. And again, remember, this is a rough estimate of your processing preferences. This is not scientific, not a clinical psychology test. But basically, the higher your score, the more your responses are consistent with people who are left brain oriented, which mean they have strengths in verbal skills, analytic thinking, processing bits of information one at a time. And the lower your score, the more your responses are consistent with right brain oriented skills, strengths in nonverbal skills, recognizing patterns, music, emotional expression, and global processing. So you could think if that kind of works in terms of your personality and what you know about your strengths and weaknesses. And some of you might be right in the middle, get a 5. And that's just kind of interesting, I think, to think about. We're going to come back to what this means again in a few minutes. Here we are with the corpus callosum again, that you've got your 2 hemispheres, and let's see. Well, look at this picture here. This is a front view of a brain. Imagine you're looking at someone straight through the front. And so we've got 2 hemispheres, and there would be a corpus callosum here connecting the 2. But it looks like in this case there was a severed corpus callosum. Here we're looking down on the brain, this picture here, picture B, looking down from the top, and you can see we've got the 2 hemispheres, and then we have some axons that are crossing, and these are that bridge, the corpus callosum. And this is a side view of the brain. The corpus callosum is this purple area, and this would be connecting the 2 sides of the brain. And again, here's a real brain, and here is the corpus callosum. This is another side view. So a hemispherectomy is the removal of nearly half the brain. You can see that here. We're missing almost half of the brain. This can be effective for eliminating and reducing seizures. Not a first choice. There are lots of medications that people try first, and this is when you've got very severe seizures that just won't go away with any other kind of treatment. So again, only used for cases where other interventions don't work. All right, so lateralization in the brain, the tendency for the left and right hemisphere to excel in certain activities. Left hemisphere tends to be lateralized or specialized for language processing. The right hemisphere is specialized for visuospatial tasks. This would be things like putting together a puzzle, putting together blocks in a way to make a pattern, etc. And so the question, you might have heard this, are people left-brained or right-brained? Well, you might have a tendency towards one kind of side of the brain or the other in terms of your particular skills, but mostly your brain works together as a team to create your experience of the world. You're not just using one side or the other. They really are working together. So let's talk about some brain areas. And when we talk about the left hemisphere, being specialized for language, there are two main language areas. We have Broca's area, which is right here. It's in the frontal lobe of the brain. And then Wernicke's area right here, we call this the temporal lobe of the brain. And we'll go through these terms again and again. But these are two important areas of the brain for language. Broca's area is important for what we call speech production. That's the ability to speak, to move your lips and your tongue and your vocal cords and everything you need to do to produce speech. And so Broca's area seems to be very important for that. Whereas Wernicke's area back here in the temporal lobe is really important for understanding speech, or what we call language comprehension. So for someone to understand what you're saying. And as you can, just as you're listening to this lecture, and maybe talking to someone in your house with you, you need both parts of your brain to be working for normal or typical language. You need to be able to understand what people are saying to you. That's Wernicke's area. And then you need to be able to produce speech, to be able to respond. That would be Broca's area. And those are both left side brain areas. In the book, you'll also read about Brandon, who had damage to his brain, and you can learn to speak again. The brain has quite a bit of plasticity, or the ability to reorganize, more so than we thought, actually. And so in the case of the girl with the hemispherectomy, you'll see as you read through the book, it's not as though she was left with being really unable to do very many things. She is able to do quite a bit, and her brain has reorganized to somehow be able to work almost without an entire hemisphere, similar to Brandon. And you'll see that, before the injury, he was able to read complex novels. Post-injury, he couldn't read very much at all. The words didn't look like letters or meaningful things anymore. And it's a long process to brain recovery. This is what a lot of my research is on children who have had strokes, and we find that brain recovery or neuroplasticity happens easier and quicker in younger individuals, and as people get older into adulthood and so on, it becomes more difficult. In terms of language, and it's related to handedness, the left hemisphere controls language in 95 to 99% of right-handed people. So if you're right-handed, it's very likely that your left hemisphere controls your language. However, with left-handed individuals, it's only 70% of people who have left hemisphere control of language. In the other 30%, language is either in their right hemisphere or in both. So it's a little more complicated in individuals with left-handed people. What about the right hemisphere? Well, this is visuospatial processing. That's the specialty of the right hemisphere. And when we say visuospatial processing, we're talking about using your brain to mentally rotate objects, understanding humor and abstract concepts, seeing faces and recognizing faces and detecting emotion. So the left hemisphere strengths, language in most people. The left hemisphere is also very good at processing details and doing analyzing and sequential processing, whereas the right hemisphere is better at spatial relationships, global processing, so looking at the big picture as opposed to the small details, and emotional processing. But really, both hemispheres work together to complete most tasks. If you think about language, not only do you need to understand the words and be able to produce the words, which is a left hemisphere task, but emotion is really important in language too. If you're missing the emotion in how someone is speaking to you, you might miss the whole meaning, right? Think about sarcasm. There's a very different meaning of the words, even if it's the exact same words. If somebody says to you, oh, that's a nice shirt, or, ooh, that's a nice shirt, right? Totally different meanings. So you need to not only understand the words, be able to produce the words, but the emotion is important too. So you can see that the right and left hemisphere are working together most of the time. I'm not going to read all of this to you. If you're interested, again, pause this video here. Left brain dominant versus right brain dominant, and can go back to that quiz that you took. These are just generalizations. They certainly don't apply to everyone, but again, you want maybe left brain dominant, more clear directions, good at analyzing problems, whereas right brain dominant, you might need to read things twice, but then you've got it. You like to write funny stories, tell about funny experiences, kind of interesting. Less scientific, I will tell you. This I kind of put in just for a little bit of fun. The global local test, now this is scientific, and I use this in my research all the time to look at individuals who have had brain damage in the right or left hemisphere. And so this is called the global local test. And as you can see here, this is an H made up of a bunch of little B's. And so if I asked a person to look at this picture, take it away, and then have them draw it, a person without any type of brain damage would draw something pretty similar to this. Now, if someone had left hemisphere damage, the left hemisphere is really good at processing details. So left hemisphere damage due to a stroke or something like that, the left hemisphere isn't working, the detail processing part of our brain isn't working. And so when I ask someone to recreate this, they may draw just a big H, right? Because the part of their brain that's working, the right hemisphere is the one that's working, that is processing the global picture, the big picture. And so basically you just get a picture of an H. Whereas if someone has right hemisphere damage, they've had a right hemisphere stroke, they are more likely, if I ask them to recreate this, not see the big picture, just see the details. And so they might draw just a bunch of little B's in no particular order. And that's a test we use all the time, a neuropsychological test, to look at right and left brain functioning. Just kind of a picture about, again, right versus left brain. The right brain more detail-oriented, more analytical, working through problems kind of piece by piece. The right brain more creative, more, again, music, emotion, all of that. And then you can see we've got this bridge, these bridges connecting, kind of like the corpus callosum, that nobody kind of uses one side or the other. We've got these connections. And you can see that this might be important if you find yourself to be really right-brained or really kind of strong in those left brain type of activities. This might be important in a career you choose or what kind of work you choose. And again, this is in here more just for interest, right? In the workplace, left hemisphere individuals that may be better at calling up customers, writing reports, making databases, things like that. The right hemisphere, people who are stronger in right hemisphere activities might be better at coming up with unusual solutions and being creative. And so you have a little response on Canvas that will be based on these ideas of lateralization. You know, even if you're a boss or a manager at work, you might think about who would be better in which kind of position based on these generalizations. To learn about lateralization, there is such a thing called a split brain operation, and this is, again, a very rare procedure that's used to disconnect the right and left hemispheres by cutting the corpus callosum. And by cutting the corpus callosum, you're preventing exchange of information between the two hemispheres. Again, this is sometimes a very, very rarely used procedure to treat severe epilepsy. When someone has epilepsy or seizures that start in one hemisphere of the brain, and they're very severe, they often will go over and affect the whole brain because the electrical activity goes across the corpus callosum. And if we can't treat that with medications, then cutting the corpus callosum is an idea to at least keep the seizures localized to half the brain. They become that, which when they only affect half the brain, they only affect half the body, and can be less frequent. Sperry and Gazzaniga were two researchers who studied split brain patients, saw they experienced fewer seizures, seemed to have normal cognitive abilities, which is pretty amazing, and no obvious changes in their temperament, personality, or general intelligence. So they really functioned quite well in the real world, but sometimes the participants behaved as if they had two separate brains and creating what we call split brain behavior, only when you really saw this in a very controlled laboratory environment. So for example, here we are looking at a patient, and we're going to talk about vision in the next lecture. But when you see things in the left visual field, so that means the left side of the world, this information goes to the right side of your brain. And information you see in the right visual field, so imagine your nose kind of is the center of what you're looking at straight ahead of you, information from your right visual field is processed by the left side of your brain. Okay? And so if you have a person who is looking straight ahead, we say look at this fixation point, which means look straight ahead and stare at that dot straight in front of you, and then present a key, picture of a key, in the left visual field. So they're still staring here, but they can see the key on their peripheral vision. It's in their left visual field. This information goes and is processed by the right hemisphere. It says, oh, that person saw a key, and then transfers over through the corpus callosum to the left hemisphere, which is where language is. And if you ask them, what did you see? The person will say, I saw a key. So the visual information is processed by the right hemisphere, transferred by the corpus callosum to the left hemisphere where those language areas are, Broca's area, right, and Wernicke's area, and the person is able to say, I saw a key. In a split brain patient, someone who'd undergone the cutting of the corpus callosum, if, again, they're looking straight ahead and the key is presented in their left visual field, that information is processed by their right hemisphere. They know they've seen this key. And if you ask them, what did you see? Because the corpus callosum is cut, they can't get that visual information to the left hemisphere, which is where the language centers are, and they can't tell you what they saw in words. They say, I don't know, I can't say it. They don't have the words because that information can't be sent over through the corpus callosum. However, if you do show the key to the right visual field, then that visual information is processed by the left hemisphere, and that's also where the language areas are, and the person is able to say the word key. Now, typically this isn't a problem because the person's eyes in the real world are moving back and forth all the time. They're not staring straight at one, fixation point. And so the information is getting into both hemispheres, and they're able to pretty much respond typically or without any difficulty in the real world. It's just in these very controlled experiments can you see the effect of not having that corpus callosum. Adaptation in the brain, as I said, my research is on neuroplasticity, or the brain's ability to heal, to grow new connections, and to reorganize, which we didn't think happened very much maybe 50 years ago. We kind of thought that once you hit about 5 years old, your brain was very static. It was how it was, and there was really no change. And we're learning now that the brain is able to change, maybe not as much as we'd like. If someone has brain damage as an adult, they're often left with significant impairments, but our research is showing that there is the ability for the brain to reorganize, and so hopefully we can learn how this happens, and hopefully we can come up with interventions to help people who have had brain injuries and strokes as adults, help them come up with interventions that would help them reorganize and